It's the Hemoglobin Challenge, episode number 2. Yes, I have found a second participant for my Hemoglobin Challenge. I'm Joel Duff, and welcome back to my channel. Coming up, correcting soft tissue fossil fibs. Our second participant, Phillip Robinson of Creation Ministries International. A really short episode today, I promise. And if you don't know what the Hemoglobin Challenge is, let me refresh your memory before we look at our second participant. The Hemoglobin Challenge was my frustration with young Earth creationists talking about how hemoglobin has been found, or whole blood cells have been found in the fossil record, giving the perception that actual hemoglobin and complete red blood cells have been found in the fossil record, when in fact the story isn't quite as sexy as that sounds. Right. And so the challenge is for young Earth creationists to present this story correctly and to not give the misimpression that something's been found that's not been found. All right. And so the example here really quickly for the hemoglobin portion is hemoglobin is a very large, complex biomolecule. All right. This molecule is found in your red blood cells, has over 11,000 atoms in one single hemoglobin molecule. A large portion of that are 4 separate proteins that are stuck together. And then there's another 300-atomed organic molecule called the heme unit. And you have several heme units as part of an entire package of hemoglobin. And so to say that hemoglobin has been found as evidence of red blood cells or blood being found in fossils is to suggest that the hemoglobin molecule is found, right? If you say like hemoglobin is found, then you're saying that this molecule here on the left has been found in a fossil, when in fact what's actually happened is none of the protein is there. All of the proteins of the globulin molecule, so in these dinosaur fossils where it's claimed that hemoglobin is found, the globin molecule is not actually there. Those amino acids are in fact decayed. And what's left is the heme unit. And the heme unit is this cyclical compound, which is very, very stable. And even the heme unit, the little arms on this heme unit here, can be modified over time, right, through a modification process, chemical biodegradation. But the central unit with the iron in the center there is extremely stable, and chemists know that it's extremely stable. And that is what's found in fossils, is the heme unit. And so what scientists are saying is they're saying they've found evidence of the remains of blood, being the hemoglobin portion of blood, evidence that hemoglobin was present, but not actually saying that hemoglobin itself is there. Now, a little tiny portion of the hemoglobin is there, a fraction of it, the heme units, are still present in sort of their original form, although, as I said, even they have been modified. So it wouldn't even be proper to say that exact heme was found that's identical to the heme that you have in your blood right now. All right, so all I'm asking is for young Earth creationists to not give the impression to their audience that these really complicated biomolecules are found in exactly the same form in fossils as they exist today in living organisms. And this was my analogy. If I told a friend that I had found a $1,000 bill while digging in my backyard, and I said, you want to see it? And I just said, hey, if I just said I found a $1,000 bill, what do you think I found? In your mind, what do you imagine that I found? You imagine that I found a $1,000 bill, right? But what I might actually be referring to is I found a very, very small portion, a degraded little tiny bit that was left of that $1,000 bill. Now, because there's some distinguishable characteristics of this little tiny bit left, I can say that this represents what was a $1,000 bill. And so I, in common parlance, might say I found a $1,000 bill, when really I found the remains of a $1,000 bill. You might say, well, that's okay. That's just the way we talk, That's not an exaggeration per se, but it is if you're talking to a naive audience and you're trying to give them the impression that things that are in the fossil record are very similar to today, and you're trying to send the message. In fact, you're not trying to. You are telling them that they're finding the same thing in the past as is in the present, and therefore there couldn't have been millions of years past, because if millions of years had passed, we wouldn't expect it to be identical. And sometimes they use that word, that they're identical, when in fact they're not identical. This little bit of $1,000 bill is not identical to having a $1,000 bill, all right? Seeing this little bit suggests that some time has passed and there's been a degradation process in play. Now that brings us to today's challenge. All right. So the new challenge goes out to Phillip Robinson of Creation Ministries International. We'll get to him in a moment. But where did I run across this particular, what piqued my interest, I guess you'd say, to me doing a second episode? I saw on Facebook this post, and I've also seen it on Twitter, I believe, as well, by Creation Ministries International. All right. A Creation Science Apologetics Ministry. And here's this Facebook post, and I'll read it to you. Discoveries of squid and octopus fossils with ink that can be reconstituted in water and used to paint call into question the idea of millions of years. Okay, so the fact that ink from a fossil squid can be used today just like it was ink then calls into question a million years. Right? Seems like a reasonable statement to make. Sounds, I would think to most audiences, like, yes, that's an interesting observation, right? These aren't new either. Famous English fossil hunter and paleontologist Mary Anning herself once painted using reconstituted ink from a fossil cephalopod ink sac. As an organic compound, ink simply doesn't last that long. Now here is where they're making a statement. Right? And this sounds like a statement of fact, doesn't it? Right? This is the logic sequence that's being presented in this little short paragraph. Found ink that's supposedly from ancient fossils, but organic compounds of which ink is made don't last very long. Therefore, this fossil can't be very old, right? I mean, even if they don't say that, that's the implication. That's what they're leading their audience to believe. But they even sort of provide that, connection for you in the next paragraph. This adds more credence to the Bible's record of Noah's flood, which rapidly buried billions of creatures and entombed them, so even purely soft creatures like jellyfish could be preserved intact. I mean, the soft tissue here of jellyfish doesn't really have anything to do with the ink, but nonetheless, the idea here is they're saying if something was preserved very, very quickly in the recent past, we might expect some of those biomolecules to still be present with us today. All right, so I read this. And I said, there's my hemoglobin challenge number 2. Now, this isn't hemoglobin. We're going to be looking at melanin. And so it's a different biomolecule, but the hemoglobin challenge is about any misuse of soft tissue, fossilization of biomolecules. So now, when I clicked on that link to read the article that was associated with this blurb in Facebook, here's what I found. So at Creation Ministries International, we have a painting, 95 million years in the making. And this article is by Phillip Robinson. And when I clicked on Phillip Robinson's name, who I've run across several times at CMI, and I think I've talked about him in the past, but Phillip Robinson, they have a little blurb about how he's like an independent writer for them, has done some projects. Doesn't say anything about his educational background. I had to do some additional searching to find out that he has a degree in education and a master's of divinity. And so he doesn't have apparently any science background, but he writes a lot of stuff on science for Creation Ministries International. Now, caveat, I believe that people can not have formal training in the sciences and yet know a lot about the sciences and have a good understanding of it. But it is at least something to consider that he doesn't have any formal training in this particular area and what he's going to talk about here. So I suspect that in this case, this is why he either misunderstands the evidence or certainly if he understands that he's misportraying the evidence from fossil ink. All right, so let's just get right down to the pertinent sense. I said I would keep this short. Let's get right down to the bulk of the important part of this particular paper. So what gives ink its color, right? So the black coloration in the ink of a cephalopod, all right, octopi and squid and so forth. It says, what gives the thing? 10% of the makeup is a biological pigment called eumelanin. And one of the two, which is one of the two forms of melanin, which is a molecule that provides pigmentation, often in feathers, skin of animals, but also in insects and other organisms. This absorbs all wavelengths of light, thus gives the squid this black color. It's made up of the creature's ink gland, which is specialized cells called melanocytes. It's true, like birds have melanocytes, in which they keep their melanin, which is the biomolecule inside of these specialized cells called melanocytes. All right, and so when they produce this this eumelanin or melanin in these melanocytes, they release that into their ink sac, and then they can push it out of their ink sac, and this is where this black pigment comes from. Note that the pigment, now they're talking about the fossil here, because they're referring to a fossil that's 95 million years old, and there is clearly black ink there in that fossil, and they can actually take that ink and they actually can like put it in water, and it looks just like you have like living squid ink there. All right, so they notice that the pigment has not been replaced during fossilization. In this and similar fossils, the eumelanin is still intact, giving the black color. In other words, the octopus ink sac contains the very same biological pigment as when the animal was alive. Right? This is a case where there's not a fossilization process. This is just a preservation process where you're preserving the molecule that was there over long periods of time. All right, now he goes on to say, Jacob Vinther, all right, lecturer in macroevolution and specialist in the preservation of melanin in fossils, admits, so here's the quote that they're going to go to an expert and say, well, here's this expert, and he says this: for decades, scientists have assumed that pigments hardly ever survive the fossilization process. This thinking is not hard to understand, as the pigment molecules should have fallen apart long ago if they were millions of years old, but they remain intact. So it all boils down to this, right? This is a foolproof argument. Biomolecules should fall apart over time. They should have fallen apart long ago. And so how could you possibly have the exact same pigment present today, 75 million years later in this fossil, right? And yet we find that they remain. So case closed, right? The Earth must be young. Right? This must have been a recent fossil and just hasn't had time for this pigment to decay and fall apart. Yet, despite their preservation, long thought impossible. Now, that's not exactly what Vinther said. He said, decades, scientists have assumed that pigments hardly ever survive. It doesn't say they never survive or can't possibly survive. It just says they hardly ever survive. I completely agree with that statement. There are many, many different kinds of pigments. Right? Pigments are just anything that absorb light, and so therefore create the colors that we see, because not every wavelength is going to be reflected, therefore creating the different appearances of colors for us. I mean, I look outside and I see a whole bunch of colorful trees right now. That is pigments that are in the leaves that are decaying, resulting in other pigments becoming more vibrant or more visible to us. That were there all along, but they were just, masked by the other pigments that were there. So there's a change in the concentration of different pigments. Right, so and those are in living cells. Those cells are living out there, and yet the pigments are decaying in them. This would seem to confirm exactly what's stated here, right? Pigments they're molecules that are not very stable, and so therefore they're going to fall apart soon after death. And so anything fossil you find with pigments in it just can't be a very old fossil. All right, let's go to Jacob Vinther's paper in Scientific American. I'll say article in Scientific American. A summary of some of his research, of which he's done a lot of research. And by the way, if you know why I get more animated about this particular topic, it's because I have a colleague that works on eumelanin, and I've had a PhD student who have graduated who worked on eumelanin, looking at fossil pigmentation in bird feathers dino bird feathers, all right, from China. And it's all about these little structures, these little organic molecules, the melanosomes, that are full of this melanin, all right, or eumelanin. and how they reflect light. And from that, we can determine the coloration of some feathers and body parts of extinct organisms. And that work, along with others, along with Jacob Vinther, who's one of the first people to really start looking at pigmentation in this way, just over the last 20 years, has revolutionized how we see what the colors of past organisms were, because we don't really have to guess in some cases now, because we actually have the preservation of some particular molecules that provided the pigmentation for these organisms. And it's the discovery of, as he says right here, the consistently superb preservation of the ink. So he's looking at these ink remains from squid and other things, made me wonder whether melanin might persist in fossils of other kinds of organisms. So less than 20 years ago, this idea of the discovery of melanin, this particular type of pigment, suddenly had scientists looking into, like, what are these pigments, how do they present color, and how stable are they? Melanin is the same pigment found in hair, skin, feathers, and eyes. It can impart red, brown, black hues, and so forth. If I could find melanin in other fossils, perhaps I could reconstruct the color of extinct animals, including dinosaurs. And that's, in fact, what's been done by he and others now. For decades, scientists have assumed that pigments hardly ever survive the fossilization process. That's the quote. All right. That's the little quote that's in the Creation Ministries International paper by Phillip Robinson. Now, I have seen this quote used in multiple different places. And so I wonder, given Phillip Robinson doesn't seem to be terribly familiar with the original materials and original research, I suspect he might have seen this particular quote in other creationist material, other people that have written about this topic. And so this is just potentially another example of where creationists read other creationist material, trust the sources, and don't understand the context, and then lift those particular things and put them yet in their article. Yes, I mean, this is what Vinther says. I mean, pigments hardly, he's building the story that prior to 2000, he's just kind of assumed that most pigments are not very stable, and therefore it'd be kind of surprising to find like the original biological pigments in fossils. But that's not a shocking statement at all. This is different than saying it's impossible. It's simply that we wouldn't necessarily have expected that without finding something that made us rethink those ideas. Well, the thing that we found that made us rethink those ideas are coloration, are actual biomolecules from ink that led to other melanosomes and so forth, and realizing, electron microscopy, there's a whole bunch of different forms of new technical ability for us to look very, very closely at molecules that make up pigmentation. So it's a relatively new field. The few known examples at that time all came from fossils of invertebrate creatures, not backbone ones. Thus, researchers could only guess at the colors of long-vanished animals, including modern ones, as a guide. As a result, dinosaur reconstructions vary widely. Some had drab earth tones, right? The original dinosaur pictures, almost all were kind of gray or brown. And now I would say we know, all right, with a fair degree of confidence that many dinosaurs were very colorful, had colorful skin pigmentation, and those that had feathers had strong pigmentation in their feathers as well. All right. Now, I want to point out that, I'll say this before this. There is a difference between the ink that is found in fossils and the ink found in present-day squid and octopi. Now, CMI makes it sound like it's the same thing. Like, you have the ink is like the same ink. You can do the same thing with it. But actually, if you look up what is in like squid ink today, there's a whole bunch of other enzymes, proteins. It's a mix of stuff. I mean, their article even suggested it was only like 10 to 40% or something like that, melanin or eumelanin, and in ink. But it's the eumelanin that gives it its color, right? That's the little pigment molecule. And that's the thing then that makes the black, right? There's a whole bunch of other stuff in ink. Now, if we were to ask the question, you go back and you look at that octopus or squid fossil from 75 million years ago, and you do the molecular analysis, and you look at what all the different biomolecules that are present in that ink, and you ask, what is there? Well, I can tell you what's there. It's melanin that's there, all right? It's this eumelanin, a particular form of melanin. That's what's present, and that's the thing that's black, and that's the thing that has the characteristics that give ink its inkiness, right? Most of its inkiness. And what's missing? Like all the other things you would find as a normal cocktail of mixtures of biomolecules that make up modern day ink. So in fact, they're not the same. The fossilization process or time has changed the ink in that fossil. What has happened is a lot of other stuff has decayed, as you would expect. There's a lot of other proteins that are not nearly as stable, as we're going to see, as melanins. And so therefore, they're all gone. 75 million years later, there's nothing else there except for the one thing that's the most stable molecule, and that is the melanin molecule. And so this is just is some diagrams of what melanin looks like. These circular compounds, they're incredibly stable molecules. And we know that from a bunch of chemistry that's done on modern melanin molecules. And eumelanin is hypothetically this thing in the middle. There's probably a lot of different, slightly different conformations to it, but all molecules like this would have this sort of characteristics. These are really stable. You notice there's something similar to this molecule and the heme molecule in hemoglobin, right? I said that all that other protein, most of the hemoglobin is gone. It's decayed, all right, in those dinosaur fossils. What's left are the most resistant to decay. And the thing about melanin is, here's what it does. Like I have some melanin in my skin, right? What's its role? It's absorbing UV, right? Ultraviolet light. And so this molecule is absorbing the energy from UV, and then it's radiating that, right? It's releasing that energy as of heat and other forms, right? And so what it's doing is it's an effective molecule for capturing energy and then releasing that energy without actually breaking down the molecule itself. Now, most molecules can't do that, right? You shine UV light on your clothing and you've got pigments in your clothing. Pretty soon your pigments are going to become faded, right? Why are they fading? Because the molecules are decaying. The pigments are falling apart because they can't handle that energy load, right? The energy you provided to it literally breaks them down, breaks the molecules apart. That's not what happens with melanin. That alone should tell you that it's a very stable molecule, right? If it's able to absorb energy and release energy, right, that's going to prevent it from being fractured and broken over time. And so the very molecule that its purpose is in living organisms gives you a hint as to why you would find it in fossils still in its original condition. So it's not fossilized. It hasn't been replaced by something else. It is the original molecules. And honestly, you'll hear like, yes, but we never knew of any fossils that lasted for millions of years. I'm sorry, what is oil? Oil's an organic compound. See, I hear creationists say all the time, like organic compounds can't survive millions of years. But no one's doubted for 100 years that oil is a long-lasting molecule, all right? The many components of oil, all right? There's an organic molecule that has a long life. And as an aside, you can find heme molecules in a lot of oil too, because they're so stable. They'll live alongside in the oil pockets. All right, so melanin is a long-lived, it's not surprising. So based on what we've learned over the last 15 years, we've learned that, in this particular case, these particular types of pigments, these colors are produced by this particular type of pigment. This pigment is very different than other pigments. And that's what's missing in the Creation Ministries International argument. They're missing two things. One is they don't mention that the ink is not the same biomolecular mixture, right? It's just melanin in the fossil, whereas modern ink has a lot of other stuff, and that's all gone. That's a significant difference, and it highlights an expectation of something that you would predict in an old, ancient fossil scenario, right? That if you have really stable molecules and you have unstable ones, then over time what you're going to see is a very different composition that you're left with. Right? So that actually contradicts the very recent age. If they were just a few thousand years ago, we would expect to see a lot of other remnants of the organic molecules of ink, not just melanin. The other thing is this whole idea that in their article, they don't mention that eumelanin is they don't mention the molecular structure of this molecule. They don't show that molecules like this, not just eumelanin, but there's some other molecules, are highly resistant to decay. And so this is not a shocking thing to find this particular molecule. Like all the other molecules of that squid are not there anymore, right? Like the rest of the squid is a rock. Like all the other portions of that squid have been replaced or disappeared, and you just have the imprint of the squid. The one thing that has survived is this eumelanin product as the original material. Because it's so incredibly stable, nothing is going to replace it. All right, so my challenge and my request is simply that that I understand Creation Ministries International and other creationists, they want to find compelling arguments for their audience that suggest that when you have two hypotheses, right? You have two worldviews. You have this idea that the world is ancient, and an idea that the world is only 4,000 years old. Those are highly contrasting views of Earth's history. And you're trying to find evidence that supports one view. This is not presenting the evidence in such a way that your audience can really judge whether it is supporting one or the other hypothesis, when you're not really presenting all the data, all the evidence. I don't think Phillip Robinson really probably understands a lot of the evidence in this particular case. I think he's just filtered this from other bad information in creationist literature and just compiled this as yet another simple argument that all biomolecules, right, organic molecules, decay. When that is an overly simplistic picture. The truth is, or the reality is that not all biomolecules are the same, and they have very different decay rates. And so I'm not shocked, not surprised to find eumelanin in fossil ink from long ago. As I said, I've gotten to see melanin myself and been able to see how it's observed and how we detect it. And it's really fascinating to be able to see a fossil and see how a bunch of other things have been extremely modified in terms of their chemical composition. And then within all this other modification to have this one molecule here, these little melanosomes, these little structures, you can think of them as like little crystals, right? But they're so incredibly stable. And I think it's really wonderful that they're actually preserved in that way, because it allows us to actually look back in time and see what color, some parts of some organisms were, because we have this actual remnant of the organic molecule still remaining. All right, that's the hemoglobin challenge number 2. Thanks for listening. We'll talk to you later. Bye-bye.